A powerful earthquake struck western China on the morning of June 16, 2026, sending seismic waves across a vast region of Asia and immediately raising questions about infrastructure located hundreds of miles and kilometers away. Among the structures that often become the focus of public attention whenever significant earthquakes occur in China is the Three Gorges Dam, the immense hydroelectric barrier spanning the Yangtze River and recognized as the largest dam in the world by installed generating capacity. The earthquake, measured at magnitude 6.3, occurred approximately 260 miles or about 418 kilometers south-southeast of Dunhuang in northwestern China. According to earthquake monitoring data, the event struck at a shallow depth of roughly 6 miles or 10 kilometers beneath the surface, a depth capable of producing strong shaking near the epicenter. The quake occurred at coordinates near 37.889 degrees north latitude and 95.403 degrees east longitude. Initial shake maps indicated severe shaking close to the source region, with maximum intensity levels reaching values associated with potentially damaging ground motion near the epicentral area. Almost immediately after reports of the earthquake appeared, a familiar question emerged. Did the shockwave travel far enough to affect the Three Gorges Dam? The question is understandable. The Three Gorges Dam occupies a unique place in the global imagination. Stretching more than 1.5 miles, or roughly 2.3 kilometers, across the Yangtze River, the structure contains tens of millions of cubic meters of concrete and supports one of the most important power generation systems on Earth. The reservoir behind it extends hundreds of miles upstream, storing an enormous volume of water. Because of its scale and strategic importance, virtually every significant earthquake in China prompts speculation about whether seismic energy might threaten the dam. Distance, however, is one of the most important factors in earthquake hazard assessment. The June 2026 earthquake occurred in Qinghai Province near the northern Tibetan Plateau region, while the Three Gorges Dam is located in Hubei Province in central China, along the Yangtze River. The straight-line separation between the earthquake source and the dam is approximately 1,000 miles, or more than 1,600 kilometers. At such distances, earthquake waves absolutely can travel through the Earth's crust. In fact, sensitive instruments around the globe detect seismic waves from earthquakes much smaller than this one. The crucial distinction is that detecting a seismic wave is very different from experiencing damaging shaking. Earthquake energy diminishes as it spreads outward from its source. Every additional mile and kilometer reduces the intensity of shaking. Geological structures, rock properties, fault geometry, and wave attenuation further weaken seismic motion as it propagates through the crust. By the time waves from a magnitude 6.3 earthquake travel more than 1,600 kilometers, the energy reaching a distant structure is dramatically reduced compared with the shaking experienced near the epicenter. This means that seismic instruments near the Three Gorges Dam may well have recorded the earthquake. Modern monitoring systems are extraordinarily sensitive. Yet the presence of a detectable seismic signal does not imply structural danger. Sensitive instruments routinely record earthquakes from distant regions of the world without those events posing any threat to large engineered structures. Understanding whether the dam faced any meaningful risk requires examining not only the distance from the earthquake, but also the geological setting beneath the dam itself. The Three Gorges Dam was not constructed on an arbitrary stretch of river. Extensive geological investigations were conducted before construction began. The dam sits on a foundation dominated by strong crystalline rock associated with the Huangling geological block, an area characterized by ancient granitic formations. Research describing the geology of the reservoir region identifies the Huangling Dome and the Zigui Basin as the principal tectonic structures in the vicinity. The dam itself was positioned on comparatively stable bedrock, capable of supporting an immense concrete gravity structure. A gravity dam functions differently from many other types of structures. Rather than relying primarily on thin walls or flexible supports, it resists water pressure through sheer mass. The enormous weight of the concrete presses downward and backward against its foundation. This basic design philosophy provides a substantial degree of inherent resistance to earthquake forces because the structure's stability derives largely from its mass and geometry. Researchers who examined seismic performance during the design and evaluation phases of the project described the Three Gorges Dam as possessing a high capability for earthquake resistance. Shaking table experiments and numerical simulations conducted on major sections of the dam indicated that the structure satisfied China's seismic design requirements for large hydraulic projects. That does not mean the dam is immune to earthquakes. No structure is completely immune. Engineers instead design critical infrastructure to withstand anticipated levels of ground motion based on regional seismic hazards. This brings attention to the fault systems surrounding the Three Gorges region. Contrary to some popular misconceptions, the dam is not situated directly atop one of China's most active major plate boundary faults. The area is considered a relatively weak seismic region compared with highly active zones such as the Tibetan Plateau, western Sichuan, or parts of Yunnan province. Historical seismic monitoring indicates that the Three Gorges reservoir area experienced relatively low levels of natural seismic activity before reservoir filling began. Nevertheless, the region contains numerous local geological structures, including faults associated with the Ziguai Basin and nearby tectonic zones. Scientific studies have identified fault systems such as the Gaoqiao Fault and the Fairy Mount Fault Zone among the geological features within the broader reservoir region. These faults are part of the complex structural framework of central China, although they generally do not produce earthquakes comparable to the largest events seen in western China. One of the most discussed seismic issues associated with the Three Gorges Dam is not distant earthquakes but reservoir-induced seismicity. Reservoir-induced seismicity occurs when the filling of a large reservoir alters stresses within the crust. The added weight of water and the movement of water into fractures can sometimes influence existing faults. This phenomenon has been documented at numerous reservoirs around the world. Studies examining seismic activity in the Three Gorges reservoir area found that earthquake patterns changed after reservoir impoundment. Many recorded events occurred close to reservoir banks and generally involved relatively small magnitudes. Researchers categorize much of this activity as being linked to local geological processes such as karst collapse, slope movement, and shallow structural adjustments rather than large tectonic ruptures. This distinction is important. The greatest seismic concern for the Three Gorges Dam is generally considered to arise from local or regional geological processes rather than a moderate earthquake occurring more than 1,000 miles away. The June 2026 earthquake originated in a tectonic environment vastly different from that of the Yangtze River Basin. Northwestern China lies within a region shaped by the continuing collision between the Indian and Eurasian tectonic plates. That continental collision has created the Tibetan Plateau, one of the most tectonically active regions on Earth. Stress generated by the collision is distributed across a complex network of faults extending through western China. The Three Gorges Dam, by contrast, lies far to the east within a much more stable interior portion of the continent. Because of this separation, the tectonic processes responsible for the Qinghai earthquake and those affecting the Three Gorges region are largely independent. The June earthquake did not occur on a fault directly connected to the geological structures beneath the dam. Public concern often stems from the enormous scale of the Three Gorges project itself. The reservoir contains vast quantities of stored water, and many people assume that any significant earthquake anywhere in China could threaten the structure. Engineering reality is more nuanced. Large dams are designed with earthquake loading in mind. Engineers analyze expected ground acceleration, seismic wave frequencies, foundation behavior, reservoir interaction effects, and structural response. These analyses consider scenarios far more severe than the weak vibrations likely to arrive from a distant magnitude 6.3 earthquake located over 1,600 kilometers away. Another factor often overlooked is frequency content. Earthquake waves contain a range of frequencies. Structures respond differently depending on their dimensions, stiffness, and natural vibration characteristics. Massive concrete gravity dams generally behave differently from tall buildings. The frequencies most damaging to skyscrapers are not necessarily the frequencies most significant for large dams. Engineers therefore evaluate seismic performance using detailed dynamic analyses rather than simple magnitude comparisons. Magnitude alone can be misleading. A magnitude 6.3 earthquake located directly beneath or near a structure may present a significant hazard. The same earthquake located more than 1,000 miles away may produce little more than a faint instrumental signal. Historical experience provides additional context. The Three Gorges region has experienced numerous distant earthquakes during the decades since the reservoir began filling. China regularly records significant earthquakes in Tibet, Qinghai, Sichuan, Xinjiang, and Yunnan. These events generate seismic waves that travel across the country. Yet the existence of those earthquakes has not automatically translated into structural damage at the dam. That does not mean monitoring agencies ignore such events. Modern dam safety programs rely on continuous surveillance. Large dams typically employ networks of instruments measuring vibration, deformation, displacement, water pressure, seepage behavior, and other indicators. Even distant earthquakes are often analyzed to verify that measured responses remain within expected limits. The question of what magnitude the Three Gorges Dam can withstand is frequently asked, but the answer is more complex than a single number. Structures are not designed simply to survive one specific magnitude. Earthquake magnitude measures energy release at the source, not shaking at the structure. The actual forces experienced by a dam depend on distance, depth, fault orientation, local geology, wave propagation, and site conditions. Consequently, a smaller nearby earthquake can produce stronger shaking than a much larger distant earthquake. Engineering studies conducted on the Three Gorges project concluded that the dam met China's seismic design standards and exhibited strong earthquake resistance characteristics during testing and simulation. Those studies focused on expected seismic hazards relevant to the dam's location, rather than hypothetical earthquakes occurring anywhere across Asia. When examining the June earthquake specifically, the available evidence points toward a straightforward conclusion. Yes, the shockwave almost certainly traveled across China. Seismic waves from a magnitude 6.3 earthquake do not simply stop after a few hundred miles. Sensitive instruments throughout the region would have been capable of detecting the event. Earthquake waves routinely travel thousands of miles and kilometers through the Earth. However, there is a substantial difference between a detectable seismic signal and a dangerous one. Given the enormous separation between the epicenter and the Three Gorges Dam, the attenuation of seismic energy over that distance, the geological stability of the dam's foundation, and the structure's earthquake-resistant design, there is no indication that the June 16th earthquake posed a significant threat to the dam itself. The broader significance of the event lies elsewhere. The earthquake serves as a reminder of China's remarkable geological diversity. The nation spans some of the most active tectonic regions on Earth, while also hosting some of the world's largest engineering projects. Western China remains subject to powerful crustal forces generated by ongoing continental collision. Central China, although comparatively stable, must still account for geological risks when constructing major infrastructure. The Three Gorges Dam occupies a unique intersection between those realities. It stands as a structure built not in a completely earthquake-free environment, but within a region where seismic considerations formed a fundamental part of its design. Every significant earthquake in China inevitably renews public scrutiny of the dam, reflecting both its immense scale and its symbolic importance. Another aspect that frequently enters discussions surrounding the Three Gorges Dam is the relationship between water reservoirs and seismic activity. The sheer size of the reservoir has led to years of scientific examination regarding whether the presence of such an enormous body of water can influence stresses within the crust. The reservoir created by the dam extends for more than 400 miles, or approximately 640 kilometers upstream. At full capacity, it contains tens of billions of cubic meters of water. Such a concentration of mass exerts measurable pressure on the Earth's crust. Scientists have long recognized that filling large reservoirs can alter underground stress conditions, particularly where pre-existing fractures and faults already exist. This phenomenon has been documented around the world. Reservoir-induced seismicity has been observed near dams in several countries, including India, the United States, China, and other regions where large artificial lakes have been created. In most cases, the earthquakes associated with these reservoirs are relatively small. They are generally measured in low magnitudes and occur close to the reservoir itself, rather than hundreds of miles away. For the Three Gorges Reservoir, seismic monitoring networks have recorded thousands of small earthquakes since the initial filling process began. The vast majority of these events have been minor and detectable primarily through instruments rather than through widespread public reports. Researchers analyzing these earthquakes found that many clustered near reservoir shorelines, steep slopes, and geological structures already known to contain faults or fractures. These observations have sometimes led to public concern that a larger earthquake could be triggered directly beneath the dam. Yet the available data indicate that seismic activity associated with the reservoir remains substantially different from the tectonic earthquakes that occur in western China. The June 2026 magnitude 6.3 earthquake illustrates that difference clearly. The earthquake near Dunhuang originated within one of Asia's major tectonic deformation zones. The forces responsible have accumulated over millions of years as the Indian plate continues pressing northward into the Eurasian plate. That continental collision has uplifted mountains, created extensive fault systems, and generated some of the strongest earthquakes recorded in modern history. The Three Gorges region is not situated within that same tectonic environment. Although faults exist beneath and around the reservoir area, the rate of crustal deformation is significantly lower than in western China. Consequently, the types of earthquakes expected in the region generally differ from those occurring near the Tibetan Plateau. This distinction becomes particularly important when considering worst-case scenarios. Public discussions often focus on a simple question. If a dam can survive one earthquake, can it survive an even larger one? Engineering assessments do not approach seismic risk in that manner. Instead, designers evaluate probable maximum ground motions expected at a particular location. These calculations incorporate regional geology, known fault systems, historical earthquake records, and statistical estimates of future seismic activity. For a structure as important as the Three Gorges Dam, the design process involved extensive seismic hazard analysis. Engineers examined potential earthquake sources within the surrounding region and modeled how shaking from those sources could affect the dam. Such studies included considerations of horizontal acceleration, vertical acceleration, foundation stability, reservoir interaction, and stress distribution throughout the concrete structure. One reason large gravity dams often perform well during earthquakes is their immense mass. The Three Gorges Dam contains approximately 27 million cubic meters of concrete. To appreciate that scale, the volume would be sufficient to fill millions of large construction trucks. This enormous weight contributes to stability during seismic events because the structure resists overturning and sliding through its own mass. That does not eliminate all earthquake risks. Engineers must also consider cracking, internal stresses, foundation movement, spillway performance, gate operations, and the behavior of auxiliary facilities. Modern dam safety programs, therefore, involve continual inspections and monitoring rather than reliance on original design calculations alone. Instrumentation throughout large dams can measure tiny movements that would be impossible to detect visually. Sensors monitor deformation, strain, temperature, water pressure, seepage, and vibration. These systems generate extensive datasets, allowing operators to identify unusual trends long before they develop into significant problems. In the case of a distant earthquake such as the June event, operators would typically review monitoring records to determine whether any unusual responses occurred. Even if instruments detected passing seismic waves, the critical question would be whether measured values remained within expected operational ranges. Distance remains the dominant factor. A useful comparison can be made with earthquakes occurring elsewhere around the globe. Powerful earthquakes in Alaska are detected by seismic stations throughout North America. Large earthquakes in Japan are recorded by instruments across Asia. Major earthquakes in South America can be measured on the opposite side of the planet. Yet these detections rarely translate into meaningful structural impacts thousands of miles away. Seismic waves are remarkably efficient travelers, but they are not immune to the laws of physics. As they spread outward from their source, energy disperses across increasingly large areas. Geological materials absorb part of that energy. Fault zones, sedimentary basins, mountain belts, and variations in crustal composition further modify wave propagation. By the time shaking from the June earthquake traveled across much of China, only a small fraction of the original energy remained. The event nevertheless highlights why earthquake monitoring remains essential throughout the country. China spans nearly 3,100 miles, or approximately 5,000 kilometers, from east to west. Within that enormous area are deserts, mountain ranges, plateaus, sedimentary basins, and some of the world's most complex tectonic systems. Earthquakes occurring in one region can provide valuable information about broader patterns of crustal stress and seismic hazard. For the Three Gorges Dam, continuous monitoring serves a dual purpose. It helps ensure the safety of the structure itself, while also contributing to scientific understanding of how large reservoirs interact with surrounding geology.